These are the answers to homework 4C. Here are the definitions that I would like you to know. Now on to question number 1. Based upon the solubility rules, predict whether each of the following ionic compounds would be soluble or insoluble in water. First compound is sodium fluoride, NaF. This compound should be soluble in water, and that's because of rule number 1 that states alkali metal ions or ammonium ions never precipitate with anything. So therefore, the sodium ion in the solution with fluoride ions would not precipitate. It would therefore be soluble. B is chromium 3 nitrate. This compound would be soluble in water because of rule number 2. Nitrate and acetate ions never precipitate with cations in solution, so the nitrate ion, if it were in the same solution with a chromium 3 ion, would not precipitate, therefore soluble. C is zinc chloride. This would be soluble based upon the third rule. Chloride ions, bromide ions, and iodide ions never precipitate with cations ever in solution except with silver ion, mercury 1 ion, and lead 2 ion. Zinc is not one of those exceptions, so zinc ions would not precipitate with chloride ions. This compound would be soluble in water. D is aluminum sulfate. This compound would be soluble in water based upon rule number 4. Sulfate ions never precipitate with cations in solution except with mercury 1, lead 2, calcium, strontium, and barium. And aluminum is not one of those exceptions, so therefore aluminum ions would not precipitate with sulfate ions. This compound would be soluble. E, calcium sulfide. This compound would be insoluble. Rule number 5 states carbonate ions, hydroxide ions, oxalate ions, phosphate ions, and sulfide ions, this is the sulfide ion here, will precipitate with all cations if they're in a solution with them, except for the alkali metal ions or ammonium. So therefore, if sulfide ions are in the same solution with calcium ions, they will form a precipitate, which is a solid. F is magnesium carbonate. This compound would be insoluble from rule number 5 for the same reason. Carbonates, hydroxides, oxalates, phosphates, and sulfides precipitate with all cations from the periodic table, except for the alkali metal ions or ammonium ions. So therefore, the carbonate ion would precipitate with the magnesium ion forming a solid. Question number 2, indicate whether a reaction will occur or not in each of the following. Writing a balanced equation is not necessary. So we were learning types of reactions that occur between pairs of compounds. These reactions are often called exchange reactions. If you have two compounds and you're trying to predict the products of a chemical reaction, you switch their partners. You make the positive ion in the first compound pair up with the negative ion in the second, then the positive ion in the second pair up with the negative ion in the first. And just because you can switch the partners, it doesn't mean a chemical reaction is going to take place. What has to happen is one of the products has to either be a precipitate, which means insoluble from the solubility rules, or water, or a gas. And so that's what we're looking for here in question number 2 to predict whether a reaction occurs. A is the reaction between solutions of calcium nitrate and aluminum chloride. If we switch the partners, we would get calcium chloride produced, CaCl2, and aluminum nitrate produced, AlNO3 taken 3 times. The solubility rules are what's going to tell us if a reaction occurs. For the first product, calcium chloride, Rule 3 says chloride ions never precipitate with any cations except silver, mercury 1, or lead. That means it will not precipitate with calcium, so calcium chloride would be a soluble ionic compound. For the aluminum nitrate, that's soluble based upon rule number 2. Nitrate ions never precipitate with any cations ever, so that would be a soluble substance also. So because we've switched the partners and we do not create a precipitate or water or a gas, that means that no reaction would occur if you mix the solutions of calcium nitrate and aluminum chloride. B, solutions of iron 2 acetate and zinc sulfate are mixed. If we write the reactants and switch their partners, the two products would be iron 2 sulfate, FeSO4, and zinc acetate, Zn, C2H3O2 taken twice. To predict if a reaction occurs or not, we have to have a product that's a solid, water, or a gas. First, for iron 2 sulfate, the fourth rule tells us sulfate ion salts never precipitate with cations unless it's with mercury 1, lead 2, or calcium, strontium, or barium. Iron is not one of those exceptions, so that means sulfate does not precipitate with iron, so this compound would be soluble, aqueous. For the second compound, zinc acetate, rule number 2, acetate ions never precipitate with cations ever, so that would be a soluble compound as well. So because on paper, when we switch the partners, but we did not produce a solid, water, or a gas, that means no reaction would occur if we mix together solutions of iron 2 acetate and zinc sulfate. 2C, solutions of sodium phosphate and aluminum bromide are mixed. If we switch the partners to predict what products there would be if a reaction occurred, we would get sodium bromide and then aluminum phosphate. First compound, sodium bromide. First rule, sodium ions, which are alkali metal ions, never precipitate with anions ever, so that has to be aqueous or soluble. For the second compound, aluminum phosphate, that's rule 5, phosphate ions precipitate with every cation on the periodic table except for the alkali metal ions or ammonium. So therefore, phosphate would precipitate in a solution that has aluminum ions, and because one of our products is a solid, that means a chemical reaction would be seen if you mix together solutions of sodium phosphate and aluminum bromide. Question number 3. Write the balanced net ionic equation for each of the following, each of which results in a reaction occurring. Indicate the phases of each reactant and product. 3A, solutions of barium acetate and nickel 2 sulfate are mixed. So a reaction with two compounds, whenever you have that, you switch the partners and you look at the products to see if you're producing a solid, water, or a gas. When we switch the partners between barium acetate and nickel 2 sulfate, the products would be BaSO4, barium sulfate, and NiC2H3O2 taken twice, nickel 2 acetate. From the solubility rules, first for the sulfate compound, barium sulfate, sulfate ions never precipitate with anything, this is rule 4, except with mercury, lead, calcium, strontium, or barium. So this is one of the rare cations that sulfate ions precipitate with, so barium sulfate would be a solid. The second compound, nickel 2 acetate, rule number 2, acetate ions never precipitate with anything, so that compound would have to be aqueous. But because the first product was a solid, that means a chemical reaction occurs. If we balance the equation, and if we check it right now, we are fortunate the equation actually is balanced the way it's written. The next thing we want to do anytime we have a reaction that has electrolytes in it is we want to write the electrolytes in a more accurate way, which means separated as their constituent ions. So the barium acetate, which is a soluble ionic compound and dissociates into ions when it dissolves, would yield a barium positive 2 ion and 2 acetate ions. The nickel 2 sulfate is soluble in water, and when ionic compounds dissolve in water, they separate into their constituent ions, so that would dissociate into a nickel 2 ion and a sulfate ion. The precipitate stays bonded together. That's why it doesn't dissolve. So BaSO4 solid written bonded together as a crystal. And the final product, nickel 2 acetate, would dissociate into a nickel 2 ion and 2 acetate ions. In this ionic equation, the 2 acetate ions and the nickel ions cancel out, leaving our net ionic equation, barium ion plus sulfate ion yields BaSO4 solid. B, sodium hydroxide and nitric acid solutions are mixed. Once again, two compounds. When you have two compounds reacting, switch the partners, and we're going to test the products to see if we're forming a solid, water, or a gas. When you react sodium hydroxide with nitric acid, the sodium goes with the nitrate to form NaNO3, sodium nitrate, and the hydrogen goes with the hydroxide, forming HOH, which is water. And because we formed water in this reaction, a chemical change takes place. This is actually an acid-base reaction that's occurring. The reaction, if we write the phases for the products, we already know the reactants are aqueous because the problem said solutions of sodium hydroxide and nitric acid are mixed. For our products, the sodium nitrate has to be soluble from either rule 1 or rule 2. Rule 1 says alkali metal ions like sodium never precipitate with anything. Rule 2 says nitrate ions never precipitate with anything, so that's aqueous. The HOH we form bonds together covalently to form a molecule, and that molecule, you should know, at room temperature exists as a liquid, so we'd write it as a liquid, and you could change its form to H2O. Because this reaction contains electrolytes, we have to write this in ionic form. The sodium hydroxide will dissociate into a sodium ion and a hydroxide ion. Nitric acid is a strong acid because it has 2 more O's than H's in its formula. That means every nitric acid molecule will ionize in solution. So we're going to get a hydrogen ion and a nitrate ion. The sodium nitrate is a soluble ionic compound that would dissociate into a sodium ion and a nitrate ion. And then the water molecule is a molecular substance. It stays H2O, liquid. In this reaction, the sodium ions are the same on the left and the right, and the nitrates are the same on the left and the right. They cancel out as spectator ions. Our net ionic equation is a hydroxide ion plus a hydrogen ion yields a water molecule. 3C, solid magnesium carbonate is added to an acetic acid solution. So we have 2 compounds again, and we're going to switch their partners. In this case, when we switch the partners, we get magnesium bonding with acetate to form MgC2H3O2 taken twice, and we get the hydrogens bonding with the carbonates, and because hydrogen is +1 and carbonate is -2, the formula has to be H2CO3. If you want this equation to be balanced, because there's 2 acetates and 2 free hydrogens on the product side, we would need a 2 in front of the acetic acid molecule on the left side. Now for phases, it said that the magnesium carbonate was a solid, so that's why I have S written on the reactant side. Acetic acid rather was a solution, so that's aqueous. On the product side, the first compound, C2H3O2, is an MgC2H3O2 taken twice, is an acetate compound, and rule 2, acetates never precipitate with anything, so that has to be aqueous. And we formed an acid, H2CO3, which is also aqueous. What you need to recognize here, seeing how there's no solid formed, there's no liquid formed, is that whenever you form H2CO3 as a product in a chemical reaction, that weak acid immediately decomposes into water and CO2. And so you have to cross it out and rewrite it as H2O liquid plus CO2 gas. So this is a reaction that occurs because you've produced water and a gas, once again another example of an acid-base reaction. Now to write this in ionic form, because we have an electrolyte in the equation. We actually have 2 electrolytes, one is strong, one is weak. Let's go through each of the reactants and products. First, magnesium carbonate is a solid. Solids stay bonded together. Leave it MgCO3 solid. Then we get to acetic acid. Acetic acid does not have 2 more O's than H's in its formula. That means it is not a strong acid, it's a weak acid. And weak acids only ionize a few percent, maybe 5% of the acetic acid molecules ionize into ions, but that means 95% of them don't. They stay bonded together in their molecular form, exactly how it's written right now. So when you have a weak acid in your equation and you're writing it in ionic form, you leave the weak acid bonded together because most of the weak acid molecules do not ionize into ions. On the product side, we have an ionic compound. This is no longer acetic acid. This is now an ionic compound, and ionic compounds that dissolve in water that are aqueous always dissociate into ions. So on the product side, we're going to write the magnesium acetate as a magnesium ion and 2 acetate ions. Water molecule is a liquid, and it exists as H2O molecules. When you drink a glass of water, you're drinking millions of water molecules. You're not drinking hydrogens and hydroxide ions. So we leave it how it's written. It's already technically correct. And carbon dioxide gas is millions of carbon dioxide gas molecules. Notice the only thing we write differently are strong electrolytes, either strong acids or soluble ionic compounds, because they exist as separated ions in solution. There are no spectator ions for this, so therefore this is the net ionic equation for C. D, solutions of ammonium sulfate and sodium hydroxide are mixed. If we write the reactants for this one, it's 2 compounds, we're going to switch the partners. If you switch the partners, the ammonium ion will go with the hydroxide ion to form NH4OH, and the sodium ion will go with the sulfate to form Na2SO4, and we would need a couple of 2's to balance the equation. But just because we can write a reaction doesn't mean that's what's going to happen. We need to form a precipitate, water, or a gas. And if we look at our 2 products, both of them are aqueous. The first compound on the product side is an ammonium ion salt. First rule, ammonium ions and alkali metal ions never precipitate with anything. Same thing for the second product, sodium sulfate, that has an alkali metal ion and it doesn't precipitate. So we finally switch the partners and we do not have a precipitate, water, or a gas. This is where you go to Plan 9 from outer space. The reaction that must be occurring is a non-obvious reaction. Erase those products, they're not correct. Go to your reactants and write the reactants in ionic form. I'm just going to dissociate the ammonium sulfate into its 2 ions and the sodium hydroxide into its 2 ions. Now, I want you to notice something I'm doing here, because this is what I'm going to always do anytime there's a non-obvious reaction. Ammonium sulfate actually would dissociate into 2 ammoniums and 1 sulfate, and the 2 NaOHs would actually make 2 sodiums and 2 hydroxides. But when you go to Plan 9, you just need to know what ions there are in the solution. It doesn't matter how many there are. So it would not be necessary to write 2 ammonium ions and 1 sulfate and 2 sodiums and 2 hydroxides. We're just trying to identify what could be reacting in this solution, so I do not carry the coefficients down. These are the 4 ions that are in the solution, and Plan 9 means look for an acid or a base. So in this reaction is the hydroxide ion, and the hydroxide ion is one of the 2 bases I want you to know. 2 things that act as Bronsted bases are the hydroxide ion and the ammonia molecule. So this is the base. Something else in the reaction must be an acid, and acids need to have hydrogens in their formula. So here's the only other substance in the equation that has a hydrogen. So the ammonium ion must be acting as an acid, and it does what a Bronsted acid does. It's going to release a hydrogen ion. The hydroxide is going to be a Bronsted base. It's going to do what Bronsted bases do and accept the hydrogen ion. And the sulfate and the sodium are spectator ions. Just erase the sulfate and the sodium. So the reaction that occurs is between the Bronsted acid and the Bronsted base. And so the acid is going to donate a hydrogen ion over to the base. So that means the base becomes water as it gains a hydrogen ion. And the ammonium ion losing a hydrogen ion becomes NH3. You could write the phase for that as either gas or aqueous, because it can dissolve in water. Either would be fine. But this is what I would consider a non-obvious reaction, because when we switched the partners, we did not produce a precipitate, water, or a gas, so it wasn't an obvious chemical reaction. We go to Plan 9, write the reactants in ionic form, and then the first type of non-obvious reaction is looking for a Bronsted acid-base reaction. We'll talk about different types of non-obvious reactions next time.